Hi there, folks. Today we're looking at logarithmic functions, or logarithms is another way referred to these. And these are just defined as being the inverse of an exponential function. And so as we start to look at these, we're literally going to think of them from that lens, from that perspective. And, these are a little bit strange for students because there is no foundation on which for you to build upon these, okay? Every other function we've kind of looked at, we already have a sense of how the operation works and how we plug things in. But with logarithms, we don't really have that sense, okay? So we don't have a lot to go on to start. We only have that they're inverses of exponential functions. And so we'll start by looking at the graphs, get a feel for what kind of values we can plug in, how these things grow and change as we plug values in. And then we'll start to convert these things back and forth between exponential and logarithmic form. Then we'll learn how to actually plug things into logarithms and get values out using our calculators, okay? So that's kind of the progression we'll go through here. And so when you look at a logarithm, it's written in this format. It's y equals log base b of x. And again, this is literally the inverse of the function y equals a times b to the x, okay? And so when you look at this thing, it's just the inverse of an exponential function. But notice it has some of the same characteristics. When you think about exponential functions, remember exponential functions, the base of an exponential function had to be greater than 0, and it couldn't be 1. And it's the same thing here for logarithms. The b value has to be greater than 0, and it can't be 1. And that's because as we learn to convert back and forth between these, the b value, the base of a logarithm, and the b value, the base of an exponential function, are literally the same thing. Okay? And so when we talk about the base of these things, we're literally talking about the same thing as we're talking about when we talk about exponential functions. So those b values are literally one and the same when we find out that we can convert back and forth between these things. And so that's why they have similar characteristics, or the same characteristics, okay? So it's y equals log base b of x. Make sure you write that b value, that base value, as a subscript. Like if it was log base 2 of x, it would be log base 2 of x. And notice how tiny that 2 is written down towards the bottom. Students get themselves in a lot of trouble because they start doing things like this. They get a little out of control with the size of that 2. And now that means something totally different. That doesn't even say log base 2 of x. That says log of 2x, okay? And that's completely different. So make sure you're writing that as a subscript. The other thing is a lot of times, and there's certain situations where we'll put this in parentheses. That's just indicating, and a lot of times the calculator needs that for us to say, hey, that thing is inside the logarithm, all right? So it knows how to calculate it correctly. You can always include the parentheses if you want, but you don't always have to have them when we're just writing these things. The calculator will almost always need you to put that thing in parentheses, so just be aware of that. So let's take a look at the graphs of these things. And again, we're going to graph this simply from the perspective of the inverse. If I look at this particular function, y equals log base 3 of x, you don't know this, but I'm going to tell you that the inverse of this thing is the function y equals 3 to the x, okay? That's the exponential function that describes the inverse of this particular logarithm. And so if I were to think about an xy chart for the inverse of this guy, and you don't even have to do an xy chart, but if I did an xy chart just so I can see some of these ordered pairs, if I plugged this in, that would be a 1/9, a 1/3, a 1, a 3, and a 9. So those are the values for the inverse, and I could even graph the inverse. You don't need to graph the inverse here. But there's a couple ways I could graph the logarithm then. So if I have this inverse, so if the inverse function, the exponential function, looks like this, well, the logarithm is going to be the same thing but reflected. And remember, we always reflect it over this y equals x line. I could also just take the values from my xy chart right here and switch the x's and the y's to get the inverse. And so if I do either one of those things, here's the values I come up with. So whether I'm reflecting them or whether I'm switching the ordered pairs, I get something that looks like this. And notice, when we go back to thinking about inverses, the inverse of a quadratic function looked like a sideways parabola, a sideways quadratic function. And here, the inverse of an exponential function kind of looks like a sideways exponential function, okay? And there's a couple key pieces to this thing. Let me get rid of all this stuff that's not the logarithm. But one of the key pieces here, one of the things we want to think about is we already knew that exponential functions typically get closer and closer to the x-axis but never touch it. Well, now we have a situation where this thing gets closer and closer to the y-axis and never touches it. Okay? And that's important because when you think about that from the perspective of domain and range for an exponential function, like exponential functions, the domain is all real numbers. You can plug anything you want into an exponential function, but the range was typically something like y is greater than 0 because we only got positive values out. We never actually touched the x-axis. Well, now because those roles are reversed, what's happening here is when I look at this graph has a domain. The domain of this graph is that x is greater than 0. In other words, logarithms cannot handle x value of 0 or x values that are negative. And that becomes important in certain situations. We can't plug 0 or negatives into logarithms. So it's just helping us to define some of the characteristics of this thing. The other thing we notice is that this thing is increasing. It's going up as I go from left to right. Just like my exponential function was increasing from left to right when I had a b value that was greater than 1, so is this guy. Look at that, a b value of 3, and it's increasing from left to right. So we're hugging the y-axis. I have a domain where x has to be greater than 0. So in other words, logarithms can't have zeros or negatives plugged in. And I see that the thing is increasing. So those are some of the characteristics we want to take away from this graph. Likewise, if I look at this one, here I have log base 1/2 of x. And again, if I think about the inverse of this thing, the inverse of this graph would be y equals 1/2 to the x power. And again, you could do this as kind of an xy chart again. And as I plug these values in, let's see, that's a 1/4, or sorry, a 4 for that one. Forgot what I was plugging in. A 2, a 1. This one is the 1/2, and this one is the 1/4. Okay? So as I plug those values in, again, if this is my inverse, so my inverse looks like this time. And again, this is not the actual graph that I want or need. This is just the inverse of this thing. I can once again reflect that over this line, or I could go back to the XY chart and just flip the ordered pairs, okay? And that might actually be easier, but I like to show you kind of the reflection here like we've been seeing. But if I start flipping each of those ordered pairs, let's see, I'd have something like this point right here. I'd have something like this point right here, and this point right here, and this one, and this one. And so I get this graph that kind of looks like a sideways exponential function. So there's that reflection. And once again, I can kind of see those same kind of characteristics. Let me erase all the stuff that's not my actual function here. So here's my logarithmic function all by itself. But notice I have those same kind of characteristics in terms of the domain. The domain of this thing is x is greater than 0. So once again, I can't plug a negative or 0 into a logarithm. That's what this graph kind of helps tell me. It also shows me that this thing is decreasing from left to right. Notice the values are going down as I go from left to right. Okay, and that's very similar to exponential functions. Right here, I had a b value of 1/2. Yeah, it's decreasing. So it has similar characteristics to the exponential functions. But again, it's hugging that y-axis. It's decreasing because of the 1/2 this time. But again, we have that domain of x is greater than 0. I can't plug negatives or zeros into logarithms. So I have some of those same characteristics. So hopefully this has given us an idea of what logarithms kind of look like and what kind of properties they might have, okay? So now let's convert back and forth between these things. So any exponential function can be written as a logarithm. Any logarithm can be written as an exponential function, okay? And so here's how the conversion works. It's really just a matter of memorizing these pieces. And I memorize it this way. I look at it and say, hey, the bases are the same. That's where I start with this thing. So that idea of b being the same for each of these. So here's the base of the logarithm and the base of the exponential function. Notice they're the same value, okay? Those are interchangeable. All right, so the base of each of them is the same. And then the other thing that I try to think about is because these are inverses, inverses tend to undo one another. They cancel each other out, which means when you think about this, from the perspective of an exponential function, exponential functions, the variable is usually the thing in the exponent. That's usually the thing we want to solve for. And look at what the logarithm version is solved for. It's solved for y. okay? And so I always just think about it as, hey, if these are inverses, they solve for one another. In other words, the logarithm should equal the exponent, okay? And so the logarithm is going to solve for it's going to equal the exponent. And then the last piece just kind of falls into place. So I start with the base is the same, the logarithm equals the exponent, what's left is what's left, okay? That's a nice way that I like to remember this thing because it makes sense in terms of the math that we're going to be doing, okay? And it helps to reinforce some of those things. For example, if I look at something like this guy, right now it's written as an exponential function, but I'm going to write it as a logarithm. So I've written it as a logarithm. I say, okay, I'm going to start with the log of base 2. I'm going to say the base is the same. And so right here, the base here was 2, so the base of my logarithm is 2. And then the next piece of this thing, I say, hey, you know what? And it equals, the logarithm should equal the exponent. So I look back to the exponential function and say, oh, the exponent was r, so the logarithm is going to equal r. And now there's only one value left, and it's the 7. Well, guess what? That goes inside my logarithm. And you could just write it as 7 here. You could put the 7 in parentheses. That would be fine as well. You don't have to have the parentheses this time. But hopefully you see why this is useful. When you look at this particular function, this is the kind of function we've solved one similar to this, but not this particular example. When we solved exponential functions, or exponential equations, we would solve them by getting common bases. When you look at this one, between a 7 and a 2, there is no common base. This is not one that I would have been able to solve previously because I couldn't get common bases. But look at what I have written right now. When I write this in the logarithmic form, look at that, it's already solved. R equals log base 2 of 7. And so the second I learn to plug this into my calculator, I'll have learned a new method for solving exponential functions. And so this exponential function right here that I wouldn't have been able to solve before, I now have the answer to it. I just need to learn how to plug that into a calculator. That's why this is important. That's why this is powerful. If you look at this particular example, y equals 5 to the second. See, this one's good in exponential format. I can see that y equals a 25. But let's see what it would look like in logarithmic form. Again, I'm going to start with the base. The base of the exponential function is right here. It's the 5. So the base of my logarithm is going to be 5. So it's log base 5. The logarithm always equals the exponent, which is 2. And now the only thing left is the y. That's what goes inside. And notice I used the parentheses this time. You don't have to have them. It's a nice habit to be in. It'll save you some headaches a little bit down the road. Okay? And so when you look at this particular example, it might be nicer to have this one in exponential form. Notice in logarithmic form, I can't do much with that y. But in exponential form, I can see exactly what y equals. And so it depends on the situation, but each format kind of has its place. If I look at this one, again, the base of this guy is a 2, so the base of my logarithm will also be 2, so log base 2. The logarithm equals the exponent, which is an n, and the only thing that's left is the 32. And once again, this is an example where once it's written in logarithmic form, I know exactly what that variable equals, okay? Now, this is one that I would have been able to do by getting common bases, so hopefully that starts to tell us something about the value of logarithms. If I look at the next one, once again, the base of this exponential function is x, so that's the base of my logarithm, so log base x. The logarithm equals the exponent, so that's a 3. The only thing left is the 10, okay? And again, I'll do parentheses this time because I kind of went back and forth here, okay? But again, the base is the same. The logarithm equals the exponent. What's left is what's left, all right? Let's go the other way. If I have these in logarithmic form, let's convert them to exponential form. I do the same thing. I say, hey, you know what? There's the base. The base is 3, so it's 3 raised to a power. And then I just have to ask, okay, what's the exponent? Is 3 raised to what exponent? Well, the logarithm equals the exponent. Right here it is, okay? So whatever the logarithm equals, that is the exponent. So it's 3 to the t power equals, well, there's only one thing left, and it's the 9. Okay, there it is in exponential form. And once again, you don't know how to plug log base 3 of 9 into your calculator yet, but you can already tell me what t equals by looking at the exponential version. Hopefully you can look at it and say, oh, t equals a 2. All right, and again, that's going to help us evaluate these things eventually. If I look at the next one, once again, the base here is a 4. So the base of my exponential function is a 4. The logarithm equals the exponent, so the exponent is a 3. So base of 4, exponent of 3. The only thing left is the m, so equals m. Done and done. And notice as an exponential function, I can finally see what m actually equals, where I couldn't see that when it was in logarithmic form. If I look at the next one, once again, the base of this one is going to be the x, so that's the base of my exponential function. The logarithm equals the exponent, that's the 2. And the only thing that's left is the 81. And again, I could tell what x is right away by looking at the exponential function. Hopefully you can look at that and say, oh, it's a 9. Okay? But now here's one of the ways that we can evaluate this. There's 2 ways that we're going to evaluate some of these things. Evaluating them by hand is just a matter of converting back and forth between exponential and logarithmic form. So we convert it to exponential form, and then we solve the exponential form. Now, granted, we can only do that some of the time. We can only do that by getting common bases. And when that doesn't work, well, then we can't evaluate it by hand. We have to use a calculator, okay? So if we want to evaluate these by hand, looking at something like this guy, I simply say, you know what? I don't know what this equals yet. Let's call it x. And now let's rewrite it as an exponential function. So this logarithm has a base of 2. It equals the exponent. The only thing that's left is the 16. So I'm just converting. I'm saying, hey, the base is the same. Here's the exponent. It equals the 16. And now we solve this the same way we've been solving this. That's 2 to the 4th power equals 2 to the x. So x equals a 4. But again, I wasn't trying to solve for x. I was trying to evaluate this. Well, this equals 4. I just evaluated that by hand. Okay, that's how we do it by hand. We can only do it some of the time. It doesn't always work. Sometimes we'll have to plug it into a calculator. Okay. This one, same kind of thing. Once again, I don't know what it equals. I'll call it x. And now I convert it. This one has a base of 3, so it's 3. The exponent is x. It's got to equal the 27. And now I just get common bases. That's 3 to the 3rd power. So x equals 3. And notice these are always ones that you can probably do in your head. Again, I wasn't trying to find x. I was trying to find the value of this guy. That's a 3. So that's how we evaluate it by hand. We evaluate it by hand by simply using our knowledge of exponential functions. Convert it and see if you can find the value when it's in exponential form. Okay? Now, that won't always be the case. Sometimes we can't get common basis, which means we can't evaluate it by hand, so we need the calculator to do this. So plugging these into the calculator requires us to be familiar with 2 special logarithms. The common logarithm, which is log base 10, and the natural logarithm, which is log base e. And the reason we have to be familiar with these is most calculators are equipped with these 2 logarithms and only these 2 logarithms. You might have a feature on your calculator that lets you punch in something like log base 3 of 25. Okay? And you can hit enter and the calculator will do the work for you. Okay? But most calculators don't have that feature. So we can't just plug that right in. We have to use the logarithms that are on the calculator. And the 2 logarithms on the calculator typically are log base 10 and log base e. All right? When we have log base 10, we call that the common logarithm. And we basically just don't ever write the 10. So anytime you see a logarithm where there's no base written, it's automatically log base 10. All right? And so when you see something like this, we'll never ever see that again. It'll always be written this way as just log of a. Okay? Likewise, if we have log base e, we don't ever write log base e. You'll never see this again. It'll always be written as ln of a. It's the logarithm natural. And the reason it's ln instead of nl is most languages, the noun and the adjective are reversed from what we are familiar with in English. So in English, it's natural logarithm, but in most other languages, it would be logarithm natural. Okay. In English, it's a blue shirt, but in most languages, it's a shirt blue. Okay. And so that's why it's ln instead of nl. All right. So logarithm natural, we'll always see it that way. And when we pull this thing up on the calculator has these 2 buttons. So here's my trusty TI calculator. Notice right in the middle here, I see an LOG button and I see an LN button. Okay. And those are log base 10 and the log base E buttons on my calculator. All right. And so here's the thing. If I just had something that said this, if it just said, hey, log of 7, that's saying log base 10 of 7. That means, hey, use this LOG button on the calculator, log of 7. And it's, you can use parentheses around that. Some calculators will automatically set up that first parenthesis. We just plug it in. There's log base 10 of 7 is 0.85. Likewise, the next one is log of 5. And I don't need the parentheses when it's just one value. But I get a 0.70 if I round that. And then this one, log base 10 of 10. It gives me a 1 on the button exactly. And that's because, sorry, I wrote a 10 there. And that's because here the log and the base the base of the logarithm and the thing inside the logarithm match. That's why that happened. And we'll see that happen throughout some of these other examples. The next one says natural log of 6. So again, natural log of 6. I just plug it right in. 1.79. So just familiarizing ourselves with these buttons. Natural log of 4. 1.39. And the natural log of e. Anytime you're trying to punch an e in, it becomes a little bit weird because most of the calculators are only equipped with an e to the power button. So I just say e to the first power, okay, is my way of doing just an e. And once again, that give me a 1. And hopefully you're looking at this going, hey, when the base and the thing inside were the same, it gave me 1. Here, the base and the thing inside were the same, it gave me 1. That's a property of logarithms, which we may discuss later. Okay. Now you might also be looking at this thinking, well, that's all well and good, but what if I have log base 5 or log base 3 or log base 7? Having only 2 logarithms on the calculator doesn't seem very useful. This is where the change of base formula comes in. Okay. We can essentially evaluate any logarithm we want with only one logarithm. I only need one logarithm on the calculator. I could have a calculator that only had the common logarithm or only had the natural logarithm, and I would be able to evaluate a logarithm of any base. Okay? And so here's what this says. It just says log base b of x equals log base a of x over log base a of b. Okay? And notice there's a mystery value that kind of popped up. Like here I did a logarithm of x over a logarithm of b. And so the question is, where in the world did a just come from? Well, a is a value of my choosing. I can pick whatever I want. In other words, I could use a value of 10 for a, which is a great choice because then it's just common log of x over the common log of b. Okay? It's always just the log of what was in there over the log of the old base. Or I could do the natural log of x over the natural log of b. Okay, I can choose any base that I want. So when it says log of a, log base a of x over log base a of b, well, a is whatever I want it to be. I just happen to choose the ones that are on the calculator, the common log or natural log. And me personally, I will always do the natural logarithm. Okay, it's just the one that tends to be more useful in the long run. Okay, for example, if I look at something like this guy is one that we could evaluate by hand. All right, so I could actually set this equal to x, and I could rewrite it, and you'd find out if you did that, you'd find out that it equals a 3. But let's plug it into the calculator. Right? For the calculator, I could just do this. I'd say, hey, the natural log of what was inside here, the 125, and it's going to be really important to close parentheses here, over the natural log of the old base, 5. Okay, that's how I do this. I just stick each of these values inside a logarithm, inside a fraction, and I divide them on my calculator. Ready? Natural log, and make sure you use parentheses, 125, close those parentheses, divided by the natural log of 5, and there it is, a 3. Okay. Likewise, if I did the common logarithm instead, ready? Common log, 125, divided by the common log of 5. Also gives me a 3. Okay. It doesn't matter if I use the natural logarithm or the common logarithm, I'm going to get the same value either way. Okay. This is our change of base formula. Okay. So anytime I want to evaluate a logarithm, it's as simple as just changing it to 2 logarithms. So here I have log base 3 of 2. I just do the natural log of 2 over the natural log of 3. Okay. It's always this guy over this guy. And I just plug them into natural logarithms, and now it's a job for my calculator. Ready? Natural log, again, close out these parentheses. That's where issues happen, over the natural log of 3. 0.63. And that's it. And hopefully what happens is you get good enough at these that I don't even need to write this as natural log of 41 over the natural log of 5. I gotta go right to plug it into my calculator. The natural log of 41, again, close those parentheses, divided by the natural log of 5. And once you get used to this, once you know how to evaluate this, this should become kind of a very simple thing that just kind of happens, all right? We don't need to write it down. We just plug it right into our calculator, and I get 2.31. And that's it. So when we're looking at logarithms, there's a couple properties that are similar to exponential functions. Watch out for those domain restrictions. I can't plug a 0 or negative into a logarithm. Think about the graphs of those as the inverse of an exponential function. Converting back and forth, we can always write an exponential function as a logarithm. We can always write a logarithm as an exponential function. And now we can evaluate these on the calculator by doing our change of base formula. Natural log of what was inside the logarithm over the natural log of the old base. Okay?